Hi everyone, I'm Jim White, and we're going to talk about water vapor and various ways that it's measured. Of course, water vapor begins with water, and we'll actually start there, but I want to give you a brief overview of what we're going to cover here. The terms you're probably the most familiar with are relative humidity and dew point temperature. And the weather forecast usually includes one or both of those. And the relative humidity is usually given in a percent of the maximum possible humidity, which depends on the temperature and pressure of the air around us. And as we cool down air that has moisture in it, we eventually reach a point where the moisture will condense into liquid water, and that's called the dew point temperature. There's also a frost point temperature. If it's very cold out, the moisture that condenses, it actually becomes frost rather than liquid water. Now, there's also what are called absolute humidity scales. These are used more in science and industry, and so you may not be as familiar with those terms. These are all what are called absolute humidity terms. And the one term that science or scientists call absolute humidity is given in grams per cubic meter. And later we'll see why that's not a very absolute term at all, or an absolute scale for moisture. The most intuitive to me is the percent moisture by volume scale. And just like we often talk about air being 70 or 80% nitrogen and 20% oxygen, well, there's always around 1% of moisture in our air mixtures at normal room conditions. So there's another term used, which is humidity ratio, which is usually use the letter W to indicate that. And that's the mass of water vapor per unit mass of dry air, or pound of water vapor per pound of dry air, gram of water vapor per gram of dry air. And then there's a term called specific humidity, and that's the weight of water per weight of mixture. So we'll get into all of these in more detail later, but first we need to talk about water. Okay, here we have some interesting facts about water. And what we have here is a temperature scale going from 0 degrees C to 374 degrees C. And there's several other interesting points on here where interesting things happen to water. At 100 degrees C, at 1 atmosphere, water boils. And at 0 degrees C and 1 atmosphere, water freezes into ice. So below 0 degrees C, we can have water in a vapor form. We can have an ice fog. We can have ice, frost, snow, and hail. So in this area here, at normal pressures, we can have water as a vapor or a liquid. And above 100 degrees C, at atmospheric pressure, all we can have is a vapor. Now, there's two very interesting points right here. This point is called the triple point, where water can exist as a liquid, a vapor, and a solid at the same time. And that's called the triple point. Triple point of water. And that happens at a very low pressure and at 0.01 degrees C. And that's actually used as a calibration point for temperature instruments. Now at 4 degrees C, liquid water reaches its highest density. So if you have a lake and slowly reduce the temperature, when you get to 4 degrees C, the water on the top starts to sink. And so this enables the water on the top to freeze, and when it freezes, it crystallizes and expands and floats. Now, if that didn't happen, ice could form anywhere, and I'm told life would be impossible on Earth except for that little phenomena associated with water. So there's another interesting point here. This is called the critical point. And at this temperature, 374 degrees C, and at 218 atmospheres, water can exist as a vapor and a liquid at the same time. And that's the area of superheated steam. And most of our electrical power generated on Earth happens up in this region with steam turbines. So that's kind of a quick view of all the interesting points of water. And of course, we live kind of down here, and this is kind of the area where relative humidity and dew points and frost points are important to us as humans. Next, I'd like to show you an interesting fact about water vapor that you might not be aware of. These are the normal constituents of dry air. And nitrogen is roughly 78% of our atmosphere. Oxygen is 21%. There's almost 1% of argon. And CO2 is 0.04%. Now, nitrogen is a diatomic molecule, which means, or a diatomic gas, I should say, that two atoms of nitrogen stick together. So the molecular weight of nitrogen is 14, so N2 is 28. It's the same way for oxygen. Two oxygen molecules oxygen atoms like to stick together. So the molecular weight of one oxygen atom is 16, but O2 is 32. Argon has a molecular weight of 40, and CO2 comes out at 44. Now, if you multiply each of these molecular weights by the percentage of their constituency, expressed as a decimal, you come up with a molecular weight of dry air of 28.9. Now water has a molecular weight of 18. That's 16 for the oxygen and then plus 2 for the hydrogens. So the density of H2O in dry air, or compared to dry air, I should say, is 18 divided by the 28.9, which is 0.622. So water vapor is only 62% as heavy as dry air. Now if we do the same thing for CO2, we find that CO2 is 1.5 times heavier than air. So this plays an important role in some of the things that water vapor will do. Okay, here's a little chemistry. We burn hydrocarbons to produce energy in a lot of different things. Propane, which we're probably familiar with, has a formula C3H8. So it's 3 carbon atoms and 8 hydrogen atoms. This is hexane, which is C6H14. So there's 6 carbon atoms, and if you add them up, there's 14 hydrogen atoms. Now when we burn hexane, we're going to get 6 molecules of carbon dioxide, CO2, and 7 molecules of water, H2O. And similar things happen with propane. You just get less CO2 and less water vapor. Now jet aircraft essentially burn kerosene. And kerosene is a mixture of long chain hydrocarbons, and each constituency of kerosene varies between a C10 and a C16. And of course, the hydrogens are connected the same way, so the amount of hydrogen will vary. So when a jet aircraft burns kerosene, it produces CO2 and water vapor. And the water vapor is what makes the contrails. Con is for condensation. But when you see the jets in the sky, as you go up in altitude, it's colder. So the hot water vapor coming out of the jet engines condenses into little droplets that we can then see. Now when they burn propane in a hot air balloon, they get carbon dioxide and water vapor. Now we know carbon dioxide is heavier than air and water vapor is lighter than air. So essentially the CO2 would want to work its way out of the bottom of the balloon, the opening at the bottom, and the water vapor would want to rise to the top in the balloon. So I think a significant amount of the lift in a hot air balloon is actually from the water vapor or steam. So next we'll look at the contrails made by kerosene from a jet airplane. To fully understand relative humidity, we have to have an understanding of partial pressures. And there's a law called Dalton's law of partial pressures. And basically what it says is the total pressure of a mixture of gases is equal to the partial pressure of each individual gas. Now, in the case of the atmosphere around us, we have 78% nitrogen and 21% oxygen. Now, nominal atmospheric pressure in terms of pounds per square inch is 14.7 psi. And for the metric people, 1 kilopascal is equal to 0.145 pounds per square inch. So in this container, which is sealed, we have 11.47 psi that comes from the nitrogen and 3 psi that comes from the oxygen. Now and there's some other gases in there, argon and neon and so forth, carbon dioxide. But if we could remove one of these gases, the pressure should go down. And I think I have an experiment that can do that. If I put some coils of copper in here that I can heat up electrically, copper will react with the oxygen to form copper oxide and copper dioxide. And we should be able to use up some of the oxygen and cause the pressure to go down. So we'll give that a try and see if that works. Well, here's our setup. I have a variable transformer known as a variac feeding a step-down transformer that can produce fairly high currents. In this jar are 2 coils of copper that I'm going to electrically heat, and hopefully the jar is sealed and I have a hose connecting to a electronic manometer, which is going to read in psi. Now what I expect to happen is when the coil's first heated, there'll be a layer of copper oxide form on the surface, and copper oxide is a pinkish goldish color, and as the copper heats further, copper dioxide will form, which is black. And this process should remove oxygen from the atmosphere in the jar. Initially, as the coil heats the air in the jar, the pressure should go up. And then after the power is turned off and everything cools down, I would expect a negative pressure due to the fact that oxygen has been removed. So let's see what happens. There, I turned on the power. There we see we're into the black oxide area, and we're at 2.9 psi and rising. Now I don't know if after the black layer forms, if it protects the copper from oxidizing further, but I'll let it run a little bit longer. I see a little bit of a red glow there. Okay, I'm going to turn the power off now. And it started to cool off in there, and the pressure's coming down. And we'll see if it goes negative. Okay, the pressure is still coming down, and I just noticed there's some of the black oxide has come off of the copper, probably as it cooled and contracted. Some of the oxide has flaked off and fallen to the bottom of the jar. The jar is still pretty warm, so this might take a while. Okay, this is worse than watching paint dry. As the pressure goes down, the rate of change is slower and slower. So about a half an hour has gone by since we turned the power off. And I'm going to turn the camera off again, and I'll turn it back on when we get a little closer to zero. Okay, we're finally approaching 0 psi. And you can always skip forward if you don't want to watch this in real time. Okay, there's finally 0. Now, will it go negative? If we've truly used up some of the oxygen in the jar, the pressure should go negative. Finally, there's a little negative pressure. So we'll let this run a while and cool off some more, and we'll come back and take another reading. Okay, about a half hour has passed, and we're at minus 0.25 psi. So I'll let it run some more and see if it goes any lower. Okay, another half hour has passed, and we've gone down a little bit more in pressure. And so I think we can call this a success. We converted some of the oxygen in the jar into copper dioxide, and that has reduced the partial pressure of oxygen in the jar. So I think that demonstrates Dalton's principle of partial pressures. So I went back several hours later, and found we had reached a negative 0.37 psi. So this means we used up approximately 10% of the oxygen in the jar to oxidize the copper. So that's my demonstration of Dalton's law. Okay, I hope at this point you understand the concept of partial pressures, and I've included a link below to some more information, and it's an important subject. So here we have the definition of percent relative humidity, which is usually abbreviated RH. And the piece of W stands for the partial pressure of the water vapor in the air. The piece of S stands for the saturation pressure. And we'll talk about that a little bit. But that ratio times 100 is the percent relative humidity. And once again, PW is the partial pressure of the water vapor, and P sub S is the saturation pressure, which is sometimes called the equilibrium pressure and is sometimes called the vapor pressure. And if you go to Wikipedia and look up water vapor pressure, you'll find a table there that gives you the vapor pressure of water at various temperatures. And at the freezing temperature, 0 degrees C, the vapor pressure of water is 0.006 atmospheres. So in a normal 1 atmosphere, that means water vapor can occupy 0.6% of the total volume of the air. At normal room temperature, the vapor pressure is 0.023, so that's 2.3% of an atmosphere. So if we were in this room and it was 100% humidity, 100% RH, 2.3% of the molecules in the air would be water vapor, assuming we had a source of water. And at the boiling temperature, the vapor pressure of water is a full 1 atmosphere. So if we had boiling water sitting here, it would be trying to fill up the room with water vapor. And if we had enough of it and things were sealed up good enough, we could actually achieve that. Now, here we have a jar with some water in it. So eventually, the molecules in the water will be trying to fill the atmosphere in the jar to a pressure that's dependent on the temperature. So if everything's at room temperature, this water wants to make this volume here 2.3% water vapor by volume. And if the jar is open and we have oxygen and nitrogen filling the volume and seal it up, the pressure will actually increase in here as the water tries to put 2.3% water vapor into that confined area. And I have a demonstration that we'll look at next that will actually show that. Before we move on to the demonstration, there's some additional points I wanted to make. The reason this is sometimes called the equilibrium pressure, that's when the vapor pressure of the water is in equilibrium with the partial pressures in this trapped volume here. And also I've added here some conversion factors if you're not familiar with a standard atmosphere. And I've also changed this last entry here to be at 86 degrees Fahrenheit or 30 degrees C. The vapor pressure of water is 0.042 atmospheres. So that means at 100% relative humidity, we could have 4.2% water vapor in this room. Now, if the water vapor's occupying 4.2% of the volume, that means we have less oxygen to breathe. So at even higher temperatures, we can get up to 7% water vapor by volume at 100% humidity. So breathing can become difficult at those kind of moisture levels. Now, if we were up here at this high temperature and high humidity and turned on the air conditioning and lowered the temperature, you'll often hear it said that the atmosphere could no longer hold that much moisture. And the temperature at which the moisture condenses out of the air is called the Dewpoint temperature. But it's not really proper to say the air can't hold that much moisture. The air's not a sponge. It's really not absorbing or holding the water vapor. It's just providing the pressure and temperature to satisfy all these partial pressure conditions. So you'll hear it over and over where people say, as the air is cooled down, the air can no longer hold that much water. And that's just a misstatement. So try to ignore that when you hear it. Okay, here's the setup for our vapor pressure demonstration. This is a homemade manometer, a liquid-filled manometer, and we have a digital manometer and a jar here. And here's a lid with 2 ports in it, and this will serve as a stopper for one of the ports. It's just a piece of hose with a brass plug in one end. And here's a little bit of distilled water and a dropper. And what we're going to do is connect up the manometers. They're both reading from the same hose. There's a T connection here. And well, let's put the lid on here. It's hard to do things with one hand. And we'll connect the hose. So there's an empty jar hooked up to a hose going to 2 different manometers. Now what I'm going to do is squirt a little bit of water into the jar and then plug it, and then we'll see what happens to the pressures. Okay, we'll plug the top. And we're seeing where the water, that little bit of water, wants to fill that volume with a partial pressure. And of course, as the pressure builds, the rate of change slows down. Now, there was already some water vapor in the jar because there's water vapor in the room. And we've had a lot of rain lately here, so if the air in the jar were dry, that is just composed of oxygen and nitrogen, we would see a bigger effect. So right now we're at 0.72 kilopascals. And we see it slowly increasing. Okay, what I'm going to do next is release the pressure. Okay, you see the manometers came down, and re-plugged the jar. Now, what happened when I released the pressure? I left some water vapor out of the jar, and some oxygen and nitrogen went in to replace it. Now I seal it again, and you see very little is happening. And that's because our partial pressures were satisfied when we plugged the jar again. So there's a little bit of increase, but basically everybody's pretty happy here. So the next step would be to dry out the jar. I'm going to dry it out with a towel inside, and then I'm going to pass air through a desiccant so that it's dry and purge the jar with dry air, and then repeat this little demonstration and see if we get more of an effect. Okay, here we have an aquarium pump, which is feeding air to this desiccant cylinder. The air goes through the desiccant and gets dried and goes into our jar, and hope you can see some bubbles coming out of there. So that's the air coming out of the jar. Well, it took two hands, so I turned off the camera to disconnect the air from the desiccant and pump. So I'm going to remove our plug and squirt in some water again, and then re-plug it and see what happens. Well, this is a slow process, so you can skip ahead here if you don't want to watch it in real time. But I think you can see we're getting more of an effect by putting dry air in the jar so that our water is supplying more of a percentage of the vapor pressure in the jar. Okay, I think that's enough to demonstrate the vapor pressure of water. Okay, after I turned the camera off, things were still going up, so I thought I'd give you another shot here. So well, it's still going up, but I guess we're not going to watch it all night. So I think that shows everything pretty good. I'm going to repeat our experiment with the dry air in the jar, and this time I'm going to squirt a lot more water in. Last time it was just a few drops, and I want to see if things progress more rapidly with more water surface area. Okay, here we go. Yes, I would say with more surface area, the evaporation is happening and pressurizing the jar much more quickly. Okay, here's an explanation of what we've just seen. Here's an open jar with some water in it. Now this water is actually boiling right now. We call this type of boiling evaporation. And as long as the partial pressure of the water vapor is less than the vapor pressure that the water wants to produce, evaporation will go on. Now in this jar, the water is not boiling. It's not evaporating because the partial pressure of the water vapor in this confined volume is equal to the vapor pressure that the water can produce. So in this case, the water vapor pressure is equal to the partial pressure of the water vapor in this upper volume. So that means we're at 100% humidity because the vapor pressure of the water is equal to the saturation pressure, and all the pressures are in equilibrium here. Now this water here will continue to boil or evaporate as long as the partial pressure above the water is less than the vapor pressure that the water molecules can produce. The rapidly vibrating water molecules are knocking some of the water molecules into the atmosphere, and some of them are actually returning to the water, but the majority of them in this case are escaping from the water. In this case, the water molecules that are escaping from the water are being replaced by water molecules condensing back into the water. Now there's a very interesting pamphlet that you can download from a manufacturer's website. It's called a Humidity Moisture Handbook. And as we go into part 2 of this moisture and humidity discussion, I suggest you download this and study it before viewing part 2. And I'll show you how to download that now. Okay, here's the website of the company that publishes the Moisture Handbook. It's www.macinstruments.com, and they make equipment for heavy industry for measuring moisture and humidity at high temperatures. And here we can access the Moisture Handbook, and you can read it right here, or right here you can download a PDF copy that you can actually print. So here's what it looks like, and it's got a wealth of information and graphs and tables, and I suggest you print this out and study it before you watch part 2 of the video on moisture. So hope to see you in part 2.